Look at this sequence of numbers: 2, 4, 8, 16, 32. What comes next? If you said 64, you recognized the pattern. Each number is double the previous one. Congratulations, you just thought like a mathematician. Now try this: 1, 1, 2, 3, 5, 8, 13. What's next? If you noticed that each number is the sum of the two before it, making the next number 21, you've just discovered the Fibonacci sequence, one of the most famous patterns in mathematics. But here's the deeper question: what's happening in your brain when you recognize these patterns? Why can some people see mathematical patterns instantly while others struggle? And most importantly, can pattern recognition be learned and improved? Welcome to Math's Whisperer, where we uncover the hidden stories of mathematics. I'm your host, and this is Season 2, Episode 8. Today, we're diving into the cognitive science of mathematical thinking to discover what separates mathematical minds from ordinary minds, and how you can develop this crucial skill that underlies all mathematical reasoning. Pattern recognition is the foundational skill of mathematical thinking. Before you can solve equations, prove theorems, or build mathematical models, you must first see the patterns that mathematics describes. And here's the good news: pattern recognition isn't a mystical talent you're born with or without. It's a skill that can be developed through practice and the right approaches. Let's start with what pattern recognition actually means in mathematical terms. A pattern is a regularity, a predictable structure, a relationship that repeats. Patterns can be visual, like the symmetry of a snowflake. They can be numerical, like the even numbers. They can be structural, like the recursive definition of factorials. They can be abstract, like the group structure in abstract algebra. The human brain is naturally pattern-seeking. Evolution wired us to find patterns because pattern recognition enhances survival. If you notice that certain berries make you sick, you recognize a pattern and avoid those berries. If you observe that prey animals gather at the watering hole at dusk, you recognize a pattern and hunt there at that time. But mathematical pattern recognition goes beyond these basic survival-oriented patterns. It involves seeing abstract relationships, mental manipulation of symbols, and recursive thinking that allows patterns within patterns. So what happens in a mathematical mind when it encounters a problem? Let's walk through an example. Suppose you're asked, what's the sum of the first 100 positive integers? That is, 1 plus 2 plus 3 plus 4, all the way up to 100. The non-mathematical approach might be to start adding. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and so on. This would work, but it's tedious and error-prone. The mathematical mind looks for a pattern. Young Carl Friedrich Gauss, according to legend, solved this problem in elementary school in seconds. How? By recognizing a pattern. He noticed that if you pair numbers from opposite ends, 1 with 100, 2 with 99, 3 with 98, each pair sums to 100, 1. Since there are 100 numbers, there are 50 such pairs. So the sum is 50 times 101, which equals 5050. This is pattern recognition in action. Gauss didn't just calculate. He saw the structural pattern that made calculation trivial. This kind of insight, seeing beyond the surface problem to the underlying structure, characterizes mathematical thinking, and it can be learned. Let's break down the cognitive skills involved in mathematical pattern recognition. First, is abstraction, the ability to strip away irrelevant details and focus on essential structure. When you look at 2, 4, 8, 16, you abstract away the specific numbers and see the relationship. Each is twice the previous. You're seeing the pattern, not just the instances. Second is generalization, extending a pattern beyond the specific cases you've observed. If you see that 2 plus 2 equals 4, and 3 plus 3 equals 6, and 4 plus 4 equals 8, you can generalize. Any number plus itself equals twice that number. You've moved from specific instances to a general rule. Third is analogy, recognizing that different problems share similar structures. If you've solved a problem about finding the area of a rectangle, and then encounter a problem about calculating the cost of carpet for a room, you recognize the analogical structure. Both involve multiplying two quantities. Fourth is recursion, seeing patterns that repeat at different scales or feed back into themselves. The Fibonacci sequence is recursive. Each term is defined by previous terms. Fractals are recursive. The same pattern appears at every level of magnification. Fifth is visualization, creating mental images of abstract relationships. Many mathematicians report seeing problems spatially, even when they're not geometric. They visualize equations as balanced scales, functions as transformations, algebraic relationships as geometric shapes. These skills interact and reinforce each other. A mathematician encountering a problem will abstract the essential elements. Look for analogies to solved problems. Generalize from specific cases. Visualize the relationships and seek recursive structure. Let's explore how this works with a classic problem: finding the area under a curve. Before calculus, this seemed impossibly hard. How do you find the area of an irregular shape? The mathematical breakthrough came from pattern recognition. Archimedes in ancient Greece had an insight: approximate the irregular area with rectangles. The more rectangles you use, the better the approximation. As the number of rectangles approaches infinity, the approximation approaches the exact area. This is pattern recognition at its finest. Archimedes saw that regular shapes, rectangles, have easily calculated areas. Many rectangles can approximate an irregular shape. Increasing rectangles improves approximation. There's a limiting pattern as rectangles approach infinity. 17 centuries later, Newton and Leibniz recognized similar patterns independently and developed calculus. They saw that many problems finding areas, calculating velocities, determining optimal values, shared the same underlying pattern of approaching a limit. This is why pattern recognition is so powerful. Once you recognize a pattern, you can apply the same solution approach to many different problems. Now, how do you develop this skill? How do you train your brain to see mathematical patterns more readily? The first technique is deliberate practice with pattern-finding exercises. Start simple. Look at number sequences and find the rule. 1, 4, 9, 16, 25. These are perfect squares. R, Sen, Wu, Ti, Shi. These are primes. 1, 3, 6, 10, 15. These are triangular numbers, sums of consecutive integers. Practice until pattern recognition becomes automatic. Your brain will start looking for patterns instinctively. Second, study classic patterns in mathematics. Familiarize yourself with arithmetic sequences, geometric sequences, exponential growth, periodic functions. The more patterns you know, the more readily you'll recognize them in new contexts. Third, practice translating between representations. Take a pattern expressed numerically and graph it. Take a geometric pattern and express it algebraically. Take a word problem and represent it symbolically. Each translation strengthens your pattern recognition across different domains. Fourth, look for invariance, things that don't change. In many problems, while specific values vary, certain relationships remain constant. Recognizing invariance often reveals the key pattern. For example, in any triangle, the sum of the angles is always 180 degrees. This invariant is a pattern that helps solve countless geometry problems. Fifth, practice working backward. Given a result, ask what pattern could produce it. If the answer to a problem is 42, what patterns of relationships among the given information lead to 42? This reverse engineering strengthens pattern recognition. Sixth, embrace productive struggle. When you don't immediately see a pattern, resist the urge to give up or look at the solution. Sit with the problem. Try different approaches. This struggle is where pattern recognition develops. Seventh, collect problem-solving strategies. Mathematicians have identified general patterns of problem-solving. Draw a diagram. Consider simpler cases. Look for symmetry. Work backward. Use contradiction. Exploit extremes. Learning these meta-patterns improves your ability to see patterns in specific problems. Let's look at how pattern recognition develops over mathematical education. Elementary students learn to recognize simple numerical patterns, counting by 2s, 5s, 10s. They see visual patterns in shapes and colors. They're building the basic neural pathways for pattern recognition. Middle school students encounter algebraic patterns, linear relationships, proportional reasoning, geometric patterns in shapes and transformations. They're learning to see patterns in more abstract symbolic forms. High school students work with functions, recognizing families of functions with shared properties. Polynomial, exponential, trigonometric, logarithmic functions each have characteristic patterns. Students learn to recognize these patterns in equations, graphs, and real-world contexts. College mathematics, students encounter abstract patterns, group structure, topological properties, vector spaces, logical patterns in proofs. They're seeing patterns in increasingly abstract and general settings. Professional mathematicians see patterns that connect different branches of mathematics. They recognize that a problem in number theory might have the same structure as a problem in topology. They see deep patterns that unite seemingly disparate areas. This progression shows that pattern recognition is developmental. Each stage builds on previous stages. You can't see abstract algebraic patterns until you've mastered numerical patterns. You can't recognize topological patterns until you understand geometric and algebraic patterns. But here's the crucial insight. Anyone can progress through these stages with appropriate practice and guidance. Mathematical talent isn't about having special pattern recognition abilities from birth. It's about developing those abilities through deliberate practice. Neuroscience supports this. Brain imaging studies show that when mathematicians solve problems, different brain regions activate than when non-mathematicians attempt the same problems. Mathematicians show greater activation in areas associated with pattern recognition, spatial reasoning, and working memory. This is key, these differences aren't innate. They develop through extensive practice. The mathematical brain is a trained brain, not a special brain. This has profound implications for mathematics education. If pattern recognition is learnable, then anyone can develop mathematical thinking. The key is providing opportunities to practice pattern recognition in appropriately challenging contexts. Unfortunately, much traditional mathematics education undermines pattern recognition. When students are given formulas to memorize and procedures to follow without understanding the underlying patterns, they don't develop pattern recognition skills. Better approaches emphasize pattern discovery. Give students sequences and ask them to find the rule. Present problems before teaching the solution method, allowing students to discover patterns themselves. Use multiple representations so students can recognize patterns across different contexts. The Socratic method works brilliantly for developing pattern recognition. Instead of telling students the answer, ask questions that guide them to discover the pattern themselves. What do you notice about these numbers? How are they changing? Can you predict what comes next? Project-based learning, where students tackle complex problems over extended periods, develops pattern recognition because real problems require seeing patterns across multiple domains. Historical approaches, showing how mathematicians discovered patterns, help students understand that pattern recognition is a process, not a flash of inspiration. Even brilliant mathematicians struggled, tried multiple approaches, and gradually recognized patterns through persistent effort. Let's examine some cognitive obstacles that interfere with pattern recognition and how to overcome them. First, functional fixedness, seeing objects or concepts only in their familiar function. If you only think of multiplication as repeated addition, you might miss patterns involving multiplicative relationships. Overcoming this requires practicing flexible thinking, looking at mathematical objects from multiple perspectives. Second, confirmation bias, looking for patterns that confirm what you already believe while ignoring contradictory evidence. A student might think all square numbers end in 1, 4, 9, or 6 because the first few do, not noticing that 25 ends in 5. Overcoming this requires checking patterns against contrexamples. Third, premature closure, settling on the first pattern you notice without checking if it's the deepest or most useful pattern. The sequence 2, 4, 8 might be doubling, or it might be powers of 2, or it might be described by other patterns. Always ask, is there a deeper pattern? Fourth, bounded thinking, failing to consider patterns outside your immediate knowledge. If you've never encountered logarithms, you won't recognize logarithmic patterns. Overcoming this requires continually expanding your mathematical knowledge. Fifth, concrete thinking difficulty with abstract patterns. Some students can see patterns in specific numbers, but struggle when those patterns are expressed algebraically. Developing this requires gradual progression from concrete to abstract. Now, let's discuss some famous examples of pattern recognition that led to major mathematical discoveries. Ramanujan, the self-taught Indian mathematician, had an almost supernatural ability to recognize patterns in numbers. He discovered thousands of mathematical identities and formulas, many of which seemed to come from pure intuition. When asked how he discovered them, He sometimes said they appeared to him in dreams. But this wasn't magic. Ramanujan spent hours daily working with numbers, writing out series, calculating sums, looking for relationships. His brain, through extensive practice, became extraordinarily attuned to numerical patterns. What seemed like intuition was actually deeply trained pattern recognition. Carl Friedrich Gauss, who we mentioned earlier, was famous for pattern recognition. Beyond the summing integers trick, Gauss discovered patterns in prime numbers, in quadratic forms, in complex numbers, in curved surfaces. His mathematical output covered an enormous range because he could see patterns others missed. Gauss's secret. He worked constantly on mathematics, exploring problems from multiple angles, looking for connections, trusting that patterns would emerge with sufficient investigation. Benoit Mandelbrot, who discovered the Mandelbrot set, recognized patterns, connecting roughness and self-similarity across different natural phenomena. He saw that coastlines, clouds, price fluctuations, and galaxy distributions shared fractal patterns. This cross-domain pattern recognition created an entirely new field. Andrew Wiles, who proved Fermat's last theorem, spent 7 years in secret working on the problem. His breakthrough came from recognizing patterns connecting elliptic curves, modular forms, and Galois representations areas that seemed unrelated. By seeing the deep pattern connecting them, he could prove what others thought impossible. These examples show that exceptional mathematical achievement comes from exceptional pattern recognition, which comes from exceptional practice and persistence. Let's end with practical exercises you can do right now to improve your pattern recognition. Exercise 1. Number sequences. Generate random sequences using different rules: arithmetic, geometric, Fibonacci type, polynomial, and practice identifying them quickly. Exercise 2. Visual patterns. Look at tessellations, fractals, and geometric designs. Identify the underlying symmetries and transformations. Exercise 3. Cross-domain translation. Take a pattern from one area, like exponential growth in population, and find analogous patterns in other areas: compound interest, radioactive decay, viral spread. Exercise for pattern creation. Don't just recognize existing patterns, create new ones. Generate a sequence following a rule you invented. This deepens understanding of pattern structure. Exercise 5. Pattern breaking. Find exceptions to patterns. Not all patterns hold universally. Learning when patterns break is as important as recognizing patterns. Exercise 6. Meta-pattern recognition. Look for patterns in your problem-solving process itself. When do you successfully recognize patterns? What approaches work best for you? The path to mathematical thinking is the path to seeing patterns everywhere. In numbers, in shapes, in logical relationships, in the structure of arguments, in the connections between ideas. When you develop pattern recognition, mathematics transforms from a collection of isolated facts and procedures into a unified landscape of interconnected ideas. You see why techniques work, not just how to apply them. You can solve unfamiliar problems because you recognize their similarity to familiar ones. You can learn new mathematics quickly because you see how it fits into existing patterns. This is what it means to think like a mathematician, to see the world as patterns waiting to be discovered, understood, and extended. If you're inspired to, Develop your mathematical thinking and pattern recognition skills. Subscribe to Math's Whisperer. We're releasing daily episodes exploring how to think mathematically, solve problems creatively, and see the hidden patterns in mathematics and the world. Tomorrow, we're meeting George Palia and learning his four-step method for solving any mathematical problemer, systematic approach that turns problem-solving from mysterious art into teachable skill. Hit subscribe, ring that bell, and comment. What patterns have you noticed in your daily life that reveal mathematical structure? Let's keep exploring mathematics together, one whisper at a time.